Okay, now we're going to cover the theory of Bernoulli's equation, and then from there we'll give a couple examples applying Bernoulli's equation to fluids, okay? So let's understand the theory behind Bernoulli's equation. We have a pipe here of a variable thickness. We have a fluid coming in here, okay, under the pressure of some source pushing it, okay, and the fluid is making its way up the tube and it's going to come out here. Over at the other hand, we have some source here pushing the fluid backwards, right? It could be that this is open to the atmosphere, so this pressure P2 can be atmospheric pressure, or it could be just some other source that's pushing this way, okay? So there's almost like a fight happening between the two sides of the tube, this side trying to push this way, this side this way. Besides that, the center of mass of the tube is also changing. The center of the tube here is here, the center of the tube here is at a certain elevation, right? So if we call this, for example, the ground, this one might be H1, and then this one might be H2, but ultimately what really matters is the difference of the heights, H2 minus H1, okay? So this is the description of Bernoulli's equation. Pressure P1 over here plus rho g H1 plus half rho V1 squared is pressure P2 plus rho g H2 plus half rho V2 squared. Where does this come from? What we're going to see is that this equation is simply just a re-expression of the mechanics equation that we know of, where we say work external is equal to change in kinetic energy plus change in potential energy. In physics 1, we talk about that equation a lot, and we say if there is some force dragging a block a certain distance, it will do a certain amount of work, and that work that it does equals to force times the distance, and that's equal to change in kinetic energy, half mv final squared minus half mv initial squared, plus change in potential energy, mgh final minus mgh initial. This equation is simply a restatement of that, right? Pressure P1 pushes it this way, and then remember what's the definition of pressure? Pressure is force over area, right? So it's the concentration of the force. So we have here P1 is equal to F1 over area 1 plus rho g H1. What is the rho represents? It's the mass of this column of liquid divided by its volume, right? So we can say here mass over volume, okay? Then this one here is going to be same, mass over volume, V1 squared. We'll write here big V. And then this is pressure P2, so this force is this way, F2 times over A2. Now we can rewrite this equation, multiply everything by V, 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 V. What happens? V cancels V, V cancels V, V cancels V, V cancels V. Then what happens here? We have force 1, volume over area 1. So if I take the volume of this one, right, divided by its area, the volume is equal to what? The area 1, right, this area 1 times the thickness here, we'll call that D1, okay? And then we can write this here, if we divide V divided by A1, we get D, right? So we get F1D, then we have here mgh1 plus half, and then the volumes cancel, mv1 squared, and then this one you have F2D2 plus mgh2 plus half mv2 squared. Now if we rewrite this as F1 minus F2, bring this one over here, okay? So you will see that we can rewrite this and make it look like exactly a mechanics problem, right? So we're going to do F1 minus F2D is equal to, then bring everything to the other side, mg H2 minus mg H1, change in potential energy, right? So it's the change in potential energy of this column of liquid which ends up over here, right? So this is the change in potential energy, And then the other part is going to be half mv2 squared minus half mv1 squared. And then this is the net work done on the fluid, right? This force is pressing this way, and this one is pressing this way, but which direction is the fluid ending up? If we already know that the fluid is flowing this way, right? Like that, therefore we already know that the fluid is going this way. That means this force is winning out on that force, right? So this force is trying to do negative work, but this one is beating that one. So the net difference of them ends up being a positive work done towards the right, okay? So we have F total external times distance d is change in potential energy plus change in kinetic energy, okay? So it becomes now like a mechanics equation, okay? Now in mechanics, we also know that an external, besides the external force, the friction can also do work, right? Works out friction. Work of friction minus mu k n d. So there could be some surface friction, normal force, and the distance d. Is there the fluid version of that? There could be, yeah. If the fluid was flowing and there was some friction along the surface here, and friction would do work, it would eat away from the energy of the system, right? But Bernoulli's equation is intended for non-viscous fluid flow. That means we're assuming that the effects of friction are negligible, okay? So Bernoulli's equation doesn't include the work done by friction. If you get more advanced in fluid dynamics and write the equation for viscous fluid flow, then you would include the frictional effects of the surface of the tube on the fluid. And then that would eat away from the energy of the system, okay? So besides the Bernoulli's equation, there's also another governing equation that we use in fluid dynamics, and that is called the equation of continuity, okay? So let's write that one and explain what that one means. Q is equal to A times V. What does that mean? So this is known as the volume flow rate. Volume flow rate. So it's the area of the tube on this side and times the velocity, okay? What's the units of that? Meter squared times meter per second, right? So it's representing the cross-sectional area of the tube. What is its area and how fast is it flowing? But when you multiply that, what do you see? You get meter cubed per second, which is a units of what? Volumes per second. So it's actually telling you how much volume of fluid is passing by a certain point per second. What's the volume flow rate? That's what this means. So we're going to assume for a lot of these problems that the fluid is incompressible, right? So we already mentioned that it's non-viscous, so frictional effects are negligible. The other thing we're going to assume is that it is incompressible. So the word is non-viscous and incompressible. Incompressible means that when you try to squeeze the fluid, right, it goes faster, right? So for incompressible fluid, what is true? Q is constant. A1 V1 is equal to A2 V2, okay? So when you try to squeeze the fluid, when you try to make the fluid area smaller, what happens to it? Its velocity goes up, right? So, for example, all other things being equal, let's say you had a tube like this, and then like this. What would happen to this? So the fluid will come like this, and you're trying to squeeze the fluid, right? And then over there, the fluid opens up again. So what does it mean to say the fluid is incompressible? From here to here, you're constricting the fluid. The area is going down. What's going to happen to the velocity? The velocity is going to go up. That means the fluid is coming at a certain rate. Let's say it's coming in at 4 meters per second. When it goes through here, it's going to jump up. Let's say 8 meters per second, right? If the area over here is let's say 10 meters squared, if the area over here is 5 meters squared, if the area gets cut in half, the velocity doubles. The fluid goes faster through that place. And then it slows down, you see? This is completely opposite to what happens on the freeway when you have a bottleneck. You have a bunch of cars coming, right? You have a bunch of cars coming, and if there's a place in the freeway that only has 2 lanes or there's construction happening, the opposite is going to happen. The car flow is going to be completely stopped. So a car flow cannot be modeled as an incompressible fluid. It is perfectly compressed. You can cause traffic to be basically halted and just stops, right? For hours you're stuck on the freeway. Why? Maybe there's some accident on the freeway on these lanes, or there's some construction happening, or there's less lanes here than over here, right? So car flow is definitely not incompressible, but fluid flow is, right? One quick example of that is that when you have a hose and you're watering your lawn, if you put your finger against the hose, at the end of the hose, there's less space for the water to come out, right? Let's say there's a tube like this and you're watering your lawn. And then when you're watering your lawn, you put your finger over here, okay? You close the space, and then there's less space for the fluid to come out, right? What happens? The water spurts out farther, right? The velocity increases. Because you're trying to constrict it, the V goes up, okay? So with the combination of the constancy of the volume flow rate and with Bernoulli's equation, we'll be able to solve a variety of different kinds of fluid flow dynamic problems, okay? So this is the foundation of fluid dynamics. Thank you very much.